Selective laser melting is an additive manufacturing process that uses 3D CAD data as a digital information source and energy in the form of a high-power laser beam, to create three-dimensional metal parts by fusing fine metal powders together. Manufacturing applications in aerospace or medical orthopedics are being pioneered. History: selective laser melting started in 1995 at the Fraunhofer Institute ILT in Aachen, Germany, with a German research project, resulting in the so-called basic ILT SLM patent DE 19,649,865. Already during its pioneering phase, Dr. Dieter Schwarz and Dr. Matthias Fuchtel from F&S Stereolithography Technik GmbH located in Paderborn collaborated with the ILT researchers Dr. Wilhelm Meiners and Dr. Konrad Wissenbach. In the early 2000s, F&S entered into a commercial partnership with MCPHEK GmbH located in Lübeck in northern Germany. Today Dr. Dieter Schwarz is with SLM Solutions GmbH and Dr. Matthias Fuchtel founded Realizer GmbH. The ASTM International F42 Standards Committee has grouped selective laser melting into the category of laser sintering, although this is an acknowledged misnomer because the process fully melts the metal into a solid homogeneous mass, unlike selective laser sintering and direct metal laser sintering, which are true sintering processes. A similar process is electron beam melting, which uses an electron beam as energy source. Process: the process starts by slicing the 3D CAD file data into layers, usually from 20 to 100 micrometers thick, creating a 2D image of each layer. This file format is the industry standard STL file used on most layer-based 3D printing or stereolithography technologies. This file is then loaded into a file preparation software package that assigns parameters, values and physical supports that allow the file to be interpreted and built by different types of additive manufacturing machines. With selective laser melting, selectively melts thin layers of atomized fine metal powder are evenly distributed using a coating mechanism onto a substrate plate, usually metal, that is fastened to an indexing table that moves in the vertical axis. This takes place inside a chamber containing a tightly controlled atmosphere of inert gas, either argon or nitrogen, at oxygen levels below 500 parts per million. Once each layer has been distributed, each 2D slice of the part geometry is fused by selectively melting the powder. This is accomplished with a high-power laser beam, usually an terbium fiber laser with hundreds of watts. The laser beam is directed in the X and Y directions with two high-frequency scanning mirrors. The laser energy is intense enough to permit full melting of the particles to form solid metal. The process is repeated layer after layer until the part is complete. Materials: most machines operate with a build chamber of 250 mm in X and Y and up to 350 mm Z, although larger machines up to 500 mm X, Y, Z and smaller machines do exist. The types of materials that can be processed include stainless steel, tool steel, cobalt chrome, titanium and aluminium. All must exist in atomized form and exhibit certain flow characteristics in order to be process capable. Applications: the types of applications most suited to the selective laser melting process are complex geometries and structures with thin walls and hidden voids or channels on the one hand or low lot sizes on the other hand. Advantage can be gained when producing hybrid forms where solid and partially formed or lattice-type geometries can be produced together to create a single object, such as a hip stem or acetabular cup or other orthopedic implant where osseointegration is enhanced by the surface geometry. Much of the pioneering work with selective laser melting technologies is on lightweight parts for aerospace where traditional manufacturing constraints, such as tooling and physical access to surfaces for machining, restrict the design of components. SLM allows parts to be built additively to form near-net shape components rather than by removing waste material. Traditional manufacturing techniques have a relatively high setup cost. While SLM has a high cost per part, it is advisable if only very few parts are to be produced. This is the case for example for spare parts of old machines or individual products like implants. Tests by NASA's Marshall Space Flight Center, which is experimenting with the technique to make some difficult-to-fabricate parts from nickel alloys for the J-2X and RS-25 rocket engines, show that difficult-to-make parts made with the technique are somewhat weaker than forged and milled parts but often avoid the need for welds which are weak points. Potential: selective laser melting or additive manufacturing, sometimes referred to as rapid manufacturing or rapid prototyping, is in its infancy with relatively few users in comparison to conventional methods such as machining, casting or forging metals, although those that are using the technology have become highly proficient. Like any process or method, selective laser melting must be suited to the task at hand. Markets such as aerospace or medical orthopedics have been evaluating the technology as a manufacturing process. Barriers to acceptance are high and compliance issues result in long periods of certification and qualification. This is demonstrated by the lack of fully formed international standards by which to measure the performance of competing systems. The standard in question is ASTM F2792-10 standard terminology for additive manufacturing technologies. See also, list of notable 3D printed weapons and parts, 3D printing, desktop manufacturing, digital fabricator, direct digital manufacturing, rapid manufacturing, selective laser sintering, solid freeform fabrication, stereolithography. References: ASTM F2792-10 standard terminology for additive manufacturing technologies, ABE, F. Costa Santos, E. Kaitamura, Y. Osakada, K. Xiaomi, M. 2003. Influence of forming conditions on the titanium model and rapid prototyping with the selective laser melting process. Proceedings of the Institution of Mechanical Engineers, Part C, Journal of Mechanical Engineering Science 217, pages 119-126. Gibson, I. Rosen, D.W. and Stucker, B. Additive Manufacturing Technologies, Rapid Prototyping to Direct Digital Manufacturing. New York, Heidelberg, Dordrecht, London, Springer. ISBN, Wallers, T. Wallers Report 2010, Additive Manufacturing State of the Industry, Annual Worldwide Progress Report. Fort Collins, Wallers Associates. Further reading, How Selective Laser Melting Works. THRE3D.com. Retrieved February 11, 2014.